So in previous video I talked about the time dilation and also the relativity of simultaneity. So in this video I am going to talk about the length contraction. So consider here we have a box in which we have a source of light A, and this source emits light and the beam of light travels along the x direction and it reaches this mirror M and it is reflected from that mirror and then it comes back at point A. So if the length of the box is L0, which is basically the rest length, now this setup is at rest. So for the complete round trip, the distance covered by the beam of light will be 2 times L0 and the speed of light is c. So therefore I can find the time interval between these two events, that is delta t naught is equal to 2 L0 by c. So now this is the time interval between these two events, that is the emission of light from A and the detection of light at A. So now we take a frame S in which this rod appears to be moving with a constant velocity v in the positive direction x. So now this is our rod, you can check in this figure. So when the light is emitted from A, then it travels towards M. So it takes some time. So let us call this time interval as delta t1. So light is emitted from A and after time delta t1 it reaches this point M. But since the frame is also moving, this rectangular setup is also moving, so it also covers an extra distance of v times delta t1, because the frame has covered an extra distance and therefore the point M has moved along positive x direction. So the distance covered by light from in this journey will be, let us call L1, and this L is basically the length of this setup, and basically in we have L0 as rest length, and now I am calling the length of this setup as L, and we will check that what is the relation between this L and L0. Okay, now I have this equation, L1 is equal to L plus V times delta T1. But you know, from the Einstein postulate, speed of light is same in all inertial frames. So therefore if the time taken by light from A to M is t1, delta t1, so the distance covered will be c time delta t1 from our simple relation S is equal to Vt. So I got this equation. So from this equation I can find a relation for time interval between these two events, and this is equal to L by C minus V. So this is the time interval between these two events. And now when the light reaches mirror M, so it is reflected back. But now you see when the light is reflected back, so it is moving along the negative x direction, while the setup or the point A is moving along the positive x direction. So therefore light has to travel less distance. So if the light takes a time delta t2 from reflecting M and reaching A, so if the time interval between these two events is delta t2, so light has to travel this less distance v delta t2, because the point A travels this distance in the x direction during this time. So if L2 is the distance covered by light in this time, so it will be equal to L2 is equal to L minus V delta T2. Again we are using the Einstein postulate, so the speed of light is same for all inertial frames. So this L2 will be equal to C times delta T2, which is equal to L minus V delta T2. So delta T2 is equal to L by C plus V. So now this is our equation 2. So delta T1 is the time for one trip and delta T2 is the prime time for the other trip. So therefore the time for the complete round trip will be delta T1 plus delta T2. So I can add these two equations. So this gives me L by C minus V plus L by C plus V. So I can take this L common and I can take the LCM, which is C squared minus V squared. So this gives me 2 times L C squared by minus V squared. So I can take this C squared common from the denominator, and it will, this one C will get cancel out with this C. So I will left with this relation. So 2L by C into 1 over 1 minus V squared by C squared. So now this is the time interval between these two events in the frame in which this setup is in motion. But in previous video we talked about time dilation, so we have obtained this relation. So if in a frame, so if delta t naught is the time interval in the rest frame and delta t is the time interval in a frame in which the setup is in motion, so we have this relation between these two time intervals. So we have derived this relation. So here we know that this delta t naught is 2L naught by C. We already done this. So using this expression I can find the time interval in the moving frame, which is 2L naught by C 1 minus V squared by C squared under the root. So this is giving me the time interval in the moving frame. Also this is also giving us the time interval in the moving frame. So here so I can equate these two equations. So this gives me delta t is equal to this delta t. So 2L by C 1 over 1 minus V squared by C squared. And this is equal to this time interval, which is 2L naught by C 1 over square root 1 minus V squared by C squared. So 2 will get cancel out on the both sides, C will get cancel out. So we will left with this relation, L over 1 minus V squared by C squared square root is equal to L naught, or L is equal to L naught 1 minus V squared by C squared under the root. Since we know that this L is the moving length, L is the length in which this frame appears to be moving, and L naught is the rest length. So this is the relation between the moving length and the this is the relation between the moving length and the rest length. Since this factor square root 1 minus V squared by C squared is always less than 1, so therefore this length L is less than L naught. So mean the moving length is contracted, or in other words the moving length appears to be contracted in a frame. We can obtain the same expression using the Lorentz transformation, and we don't need to worry about the geometry of the figures. So now it is very simple. So consider we have a rod, and this rod is moving in a frame S with speed V along the positive x direction, as you can see in this figure. So if I define a frame S prime, and this S prime is also moving with the rod with the same speed, so in this frame this rod is in rest. So therefore this x2 prime minus x1 prime will be the length of the rod. So in S prime frame, rod is at rest, so the rest length of this rod is x2 prime minus x1 prime, which I am calling L naught. So now we have two events. So events event 1 is the measurement of the left end of the rod, and event E2 is the measurement of the right end of the rod. So in S frame this rod is in moving, so therefore we have to measure these two lengths or these two edges at the same time. So mean E1 and E2 are simultaneous in time. Because rod is moving, if we don't measure at the same time, then of course due to motion there will be extra distance. So I can write the coordinates. So x1 y1 z1 t, x2 y2 z2 and t, because the events are simultaneous in time. And in S prime frame I can write the coordinate x1 prime y1 prime z1 prime and t1 prime, x2 prime y2 prime z2 prime and t2 prime. So in the rest frame, so there is no condition that we should have a simultaneous measurements. because if the rod is at rest, so first we can measure the left end and then we can measure the right end, so there is no restriction. So now we can use the Lorentz transformation equation. We have obtained the Lorentz transformation equation in the previous video, so you can find a link in the description. So this is how we can transform the x coordinate from one frame to another frame. So x2 prime will be the corresponding x coordinate in the rest frame, so this will be x2 minus vt divided by 1 minus v squared by c squared. So this is x2. Similarly we can find x1 prime, so this will give me x1 minus vt divided by 1 minus v squared by c squared. So x2 prime minus x1 prime will be equal to, so we can subtract these two equations. Since we have the minus vt plus vt, so this will get cancelled out, so we will left with x2 minus x1 1 minus v squared by c squared under the root. But this x2 prime minus x1 prime is the rest length, because in s prime frame rod is in rest. So therefore this is L0 is equal to, so if I call x2 minus x1 the length of the rod in the frame in which it is moving, so it is L. So this gives me relation L0 is equal to L divided by square root 1 minus v squared by c squared. Since this factor 1 over 1 minus v squared by c squared is always less than 1, so therefore L0 is greater than L, mean that the rest length is the maximum length possible. Or we can shift it another side, so we can say that L is equal to L0 into 1 minus v squared by c squared. So moving length is equal to rest length multiplied by this factor. So now you have seen that from the Lorentz transformation equation we can easily find the length contraction formula. So that is all for this video. So thanks for watching.